Hello and welcome to today's video lecture on three fundamental concepts in semiconductor physics that are Fermi level, drift and diffusion current. In my first lecture, I have discussed about semiconductor, its properties and its applications. Now, in this lecture, we will discuss about the Fermi level, drift and diffusion current. These concepts form the bedrock of our understanding of semiconductor behavior, influencing the design and functionality of electronic devices that have become integral to our daily lives. So let's start with the Fermi level. I just give you one by one basic concepts, then I will go to the each and every slide. So first start with the Fermi level, a concept named after the renowned physicist Enrico Fermi, sorry. The Fermi level represents the energy level at which electrons in a material have a 50% probability of being occupied at absolute zero temperature. So in simple terms, we can say that it serves as a reference point for understanding the distribution of electrons in semiconductor. At absolute zero, the Fermi level is a fixed energy level within the energy band gap. Now comes to the drift current. So drift current is the flow of charge carriers, either electrons or holes, in response to an electric field. When a voltage is applied across a semiconductor material, an electric field is created, causing charged particles to move. Electrons being negatively charged move into the opposite direction of the field, while holes or positive charge carriers move with the same field. This movement constitutes drift current, a crucial mechanism in the operation of electronic devices such as transistors and diodes. Now let's delve into diffusion current. Diffusion current arises due to the concentration gradient of charge carriers in a semiconductor. In regions where there is a difference in carrier concentration, carriers tend to move from areas of higher concentration to lower concentration. So this movement results in a diffusion of charge carriers and gives rise to the diffusion current. So diffusion current is particularly significant in the context of PN junction, which are central to the operation of diodes and other semiconductor devices. To visualize these concepts, we just consider a semiconductor device under the influence of both an electric field and concentration gradient. The interplay between these two mechanisms is crucial for the proper functioning of many semiconductor devices. Now, in conclusion, the Fermi level, drift, diffusion are foundational concepts in semiconductor physics, providing the framework for comprehending the behavior of charge carriers in semiconductor materials. As we continue to advance in semiconductor technology, a deep understanding of these principles become increasingly crucial for innovating and pushing the boundaries of electronic devices that shape our interconnected world. Now, starting with the Fermi level, so definitely this Fermi level is depending on the Fermi-Dirac statistics. So that is the basic physics. Fermi-Dirac statistics, the following considerations are used in the development of the statistics. Number one, indistinguishability of the electrons. Okay, that is the half spin integer. Next, electron wave nature. And the third, it's called Pauli exclusion principle. Now, what is Pauli exclusion principle? You have to distinguish these electrons into the same axis. So, electrons are moving into the opposite half integer spin. So that is actually the Pauli's exclusion principle of that. Now, what is the equation here? As you can see, the equation of f of e is the Fermi-Dirac statistics, that is 1 by 1 plus exponential e minus ef divided by kt. E minus ef divided by kt. So E is the, as you can see, the total energy level. F of E is the Fermi-Dirac distribution function. EF is called the Fermi level that represents an important quantity in the analysis of semiconductor behavior. So for an energy like E is equals to EF, the occupation probability is F of EF is equals to 1 by 1 plus 1, that is equals to half. Okay, it's equals to half. Now, how it's equals to half? That means when E is equals to EF, if EF minus EF, that is 0, so 0 by KT means 0, and e to the power 0 is 1. So 1 by 1 plus 1, that is equals to half. That means 50% probability that an electron occupy the certain level. Now that is called the Fermi level. And what is K? K is the Boltzmann's constant, and the unit is given, that is fixed, 8.62 10 to the minus 5 electron volt per Kelvin, or 1.38 into 10 to the minus 23 joule per Kelvin. Sorry. Now that is the Fermi level. Now, how you can set that 0, half, and 1, this standard? If E is equals to EF, that means we know that this is called half probability. Okay, but if it's like E less than EF, E less than EF, that means it's like 1 by 1 plus 0, so that is 1. E is less than EF. See, if you can consider this equation, then E less than EF. If E is less than EF, that means that is positive. So 1 and E greater than EF. If it's E greater than EF, then it's positive. So before the E less than EF, it's negative, and E greater than EF is positive. In this way, you can consider this value 0, half, and 1. So that is all about T is equals to 0 Kelvin. Okay, T is equals to 0 Kelvin. Now, at 0 Kelvin, available energy state up to EF is filled with electrons, and all states about EF are empty. Now, when you increase the temperature, that is T greater than 0 Kelvin, T greater than 0 Kelvin, suppose 50 Kelvin, 100 Kelvin, 150 Kelvin, as you can see from the topmost level, it's reducing, and from the low level, it's increasing. So there is a slope. As you can see that from the topmost level, it's reducing, but from the low level, it's increasing. So the function, that is E and the f of E, the function of E, when you can consider, then at temperatures higher than 0 Kelvin, some probability f of E exists for states above the Fermi level, that is to be filled with electrons, and there is a corresponding probability like 1 minus f of E, that states below EF or Fermi level that are empty. Okay. So we can conclude this Fermi-Dirac distribution function that uh, the Fermi function is symmetrical about EF for all temperatures. The probability exists for state delta E, that above EF is filled F of EF plus delta E, and 1 minus F of EF minus delta E, that delta E below EF is filled. Now, this is the practical measurement or scenario. As you can see, that effect of temperature that on Fermi-Dirac distribution function, where you can see T is equals to 100 Kelvin to 400 Kelvin, you can see the distribution. So from the highest level, it's reducing continuously, and from the lower level, it's increasing continuously. Now, that is the relation between f of E and the band structure. And uh, first picture, that is for intrinsic semiconductor. Here you can see valence band, conduction band energy, and Fermi level energies. Fermi level energy is absolutely in middle between the valence band and conduction band energy. Okay, so there is a 50% probability that an electron can occupy the certain level. But if it's n-type material, n-type means, in the previous lecture we have discussed about the extrinsic semiconductor material, where the phosphorus is doped with silicon. That means that is the pentavalent. So one electron is extra at the valence shell. Now, if one electron is extra, so definitely your Fermi energy level is very near to the conduction band, because that electron's probability that's lying, it's very near to the conduction band for this n-type material. But for p-type material, it's near to the valence band, because that is positive. So, sorry, holes are generated. There is the group 3 elements, either boron or aluminium. So that is very near to the valence band, you can see. Now these are the distribution for intrinsic and extrinsic semiconductor material. And if the electron probability is f of e, then hole probability is definitely 1 minus f of e. So the Fermi level at the conclusion, we can say that that is the based on probability distribution function in mathematics, PDF. And the probability that an available state at an energy E will be occupied by an electron f of E is equals to 1 by 1 plus e to the power E minus EF by KT. So this is the equation of any Fermi-Dirac distribution function. And next, the band diagram. The band diagram revisited that conduction band. You can see a lowest energy state for a free electron. So electrons in the conduction band means current can flow. Electrons in the conduction band, that will be treated like a free charge carriers. So that electrons are again trying to shift to the valence band for recombination. So when energy is released, that is Eg is equals to h nu or hc by lambda. And at that point, due to the velocity, your current is produced. Now, in the valence band, highest energy state for filled outer cells, holes in the valence band means current can flow. This is the picture, that is very middle to in between valence band and conduction band. That is a half or 50% probability that an electron can occupy the level. Effect of doping on Fermi level, that is n-type material, that is very near to the conduction band, what I have mentioned already, just a summary. So high probability of a free electron in the conduction band, so moving EF closer to the EC, that is conduction band energy, that is higher doping. Similarly, for the valence band, p-type material, it's very near to that, and low probability of a free electron in the conduction band and high probability of holes in the valence band. And this is a very clear summary of probability of occupancy versus energy of the Fermi-Dirac, the Bose-Einstein, and the Maxwell-Boltzmann distribution. If we can put the different parameters, then we can see we have already experimented, and we can see the result that if I can put E minus EF value is 0.02 eV, and temperature T I just set as the normal or room temperature, that is 300 Kelvin, then Emax, it's just I set the value that 0.2 to minus 0.2, then calculated occupancy probability is Maxwell-Boltzmann is almost 46%, whereas Fermi-Dirac distribution is 32% and Bose-Einstein distribution is the 86%. As we can see, the result that all three functions are almost equal for large energies, more than a few kT, that is multiply by Boltzmann constant and the temperature, that beyond the Fermi energy, the Fermi-Dirac distribution reaches a maximum of 100% for energies which are a few kT below the Fermi energy, while the Bose-Einstein distribution diverges at the Fermi energy and has no validity for energies below the Fermi energy. So that's the comparison between the three distributions, where you can see the Fermi-Dirac distribution is most fitted compared to the Bose-Einstein and the Maxwell-Boltzmann distribution. So the electron and hole concentration at equilibrium, where N0 is equals to EC to the power infinity, EC and infinity like conduction band energy, and F of E Ne into dE. Now what is NE dE? NE dE is the density of states in the energy range, that is dE, small energy displacement. The subscript 0 used for the electron and hole concentration symbols indicate equilibrium conditions. If it's in equilibrium conditions, that's why I put 0 over here, N0. If it's electron concentration in equilibrium, it's N0. If it's hole concentration in equilibrium, that is P0. And the number of electrons per unit volume in energy range, that is dE, is the product of the density of states and the probability of occupancy F of E. F of E is nothing but a Fermi-Dirac distribution function, and NED is the density of states. So NE is proportional to e to the power half. So the density of states, we can say that in the conduction band increases with electron energy. Now, this is the summary that intrinsic semiconductor, N-type semiconductor and P-type semiconductor, where the concentration level, as you can see very clearly, that for intrinsic, both the concentration level for electrons and holes are same, but where your N-type semiconductor, near to the conduction band, the concentration level is much more higher than the near to the valence band, just opposite in the P-type semiconductor for that. Charge neutrality relationship, where if you consider the donor concentration level and acceptor concentration level, then if that is your electrical neutrality stage, so law of electrical neutrality says that P minus N, that is, I just put that as a hashtag of carriers, the positive and the negative charge carriers, plus Nd minus Na, that is the hashtag of ions, that equals to 0. So for uniformly doped semiconductor, assuming the total ionization of dopant atoms, the total charge is equals to 0 if you consider the carriers and the ions for positive and negative charge carriers. So if that is your heavily one-sided doping, Nd minus Na is of course almost equals to Nd, that is almost equals to donor concentration level. If it's the N type, so Nd is very greater than of Na, so N is almost equals to Nd, and P is almost equals to Ni square by Nd, because N into P is equals to Ni square, that is the mass action law. Okay, the under thermal equilibrium, the product of the number of electrons and the number of holes is equals to the square of intrinsic carrier concentration. So Ni is nothing but an intrinsic carrier concentration, and the opposite if acceptor atoms, so Na is all very greater than of Nd, so that P is almost equals to Na and N almost equals to Ni square by Na. So we can say from that equations that doped semiconductor where Ni or intrinsic carrier concentration is very greater than of Nd minus Na or Na minus Nd, whatever. That means increasing temperature increases the number of intrinsic carriers. All semiconductors become intrinsic at sufficiently high temperature. So N almost equals to P, it's almost equals to intrinsic carrier concentration levels. That is for only the intrinsic concentration. Now coming to the next part after Fermi level and the positions of the carriers, thermal motion of charged particles that look at drift and diffusion in silicon. So assume that is the one-dimensional motion. And where you can apply this, that definitely you can apply for the both electronics and biological systems, these motions. So starting with the drift of carriers. Drift of carriers, the free electrons inside a semiconductor that move randomly due to their thermal energy, and this random movement does not produce any resultant current. However, application of an external electric field will cause the drift of electrons. So let Vd suppose is the drift velocity. So Vd is equals to mu n into E. You can see that Vd is equals to mu n into E, and if we can consider the resultant current density, then that is Jn is equals to n into Q into V into D. Now you can see the right side picture, that is a semiconductor crystal where silicons are tightly bound with the neighboring atoms. Let's make the proper covalent bonds. Now when under applied electric field, you can see that this random movements under the crystals, the carrier. So that is the, it's called the movement of charged particles in response to an external field. That is called the drift velocity. So drift velocity, what I have mentioned, that the Vd is equals to mu n into E under applied electric field. Okay, and Jn, that is the resultant current density, Jn is equals to n into Q into Vd. N into Q into Vd, that means we can write easily n into Q into mu n into E. Okay, so that I mentioned here, that Jn drift, that is n into Q into mu n into E, and if it's Jp, then it is P into Q into mu into E. P into Q into mu P into E if it's Jp. Okay, resultant current density, that current due to drift of holes and current due to drift of electrons. Okay, so total drift current, that J is equals to Jn plus Jp. Total drift current, that J is equals to Jn plus Jp, where we can write that Q into n into mu n plus P into mu P into E. Okay, so we can write easily that this is called sigma into E, because Q into uh, n into mu n plus P into mu P, this is nothing but the conductivity. Okay, which is the conductivity. Now, resistivity is very closely related to the carrier drift, and that is inversely proportional, proportionally constant between electric field and the total particle current flow. So n type, that is rho is equals to 1 by q into mu n into nd, and for p type rho is equals to 1 by q into mu p into na. Next, what is diffusion? The diffusion is the in addition, like to drift mechanism, we can say that transport of carriers in a semiconductor that occurs due to another mechanism is called diffusion, where due to the property of diffusion, we can say the excess of carriers will diffuse from the side of greater or the higher concentration level to the lower concentration levels. Okay, so charged particles move in random directions. Charged particles tend to move from areas of higher concentration to lower concentration. That is definitely the second law of thermodynamics. And net effect is a current flow, that Jn diffusion, as we can see, Q into dn by dx. Now, what is dn? Dn is the diffusion constant for electrons, that is meter square per second, that is dn. Q is the charge, okay, electron charge. Dn by dx. Now, what is dn by dx? That is electron concentration gradient. Dn by dx is the electron concentration gradient. Similarly, the Jp diffusion is Q into dp by dx. Dp is the diffusion constant for holes, and dp by dx is the hole concentration gradient. Now, why the negative sign is there? It's very important from the only the JP diffusion part. The negative sign in the expression of JP indicates that JP has a direction towards the decreasing hole concentration. Decreasing hole concentration. If I can draw this graph, that is either QN or QP, okay, and this is the displacement. Suppose x is the distance, and here your suppose x is 0, then this is the exponential curve, and you can say that this is the direction of P, the similar direction of JP. Similarly, if is the direction of N, the opposite direction is that is the current direction is definitely the opposite direction of the electrons, that is Jn. Okay, so JP diffusion is negative because its concentration is from higher to lower. That's why the sign is negative. But for Jn, that is from lower to higher, that's why is positive. Okay. So the negative sign here in mention that JP diffusion is due to moving the opposite direction from the concentration gradient. So the summary that yes, uh, we have to produce current. So finally, we have to determine the total current equation. So summation of both drift and diffusion, that Jn is equals to Jn drift plus Jn diffusion, right? And this is the Jn drift equation. I have already mentioned earlier, mu n into Qn, Q into n into E, plus Jn diffusion, the equation, that is the Jn diffusion equation, that Q into Dn to dn by dx. That is for one dimension. I have already mentioned that we are calculating that is for one dimension, and this one is for JP, JP drift plus JP diffusion. Accordingly, the same equation for one dimension, and the total current flow J is equals to Jn plus GP. So you can easily write this two expression, combination of this two expression, that is the total current in the semiconductor. You can calculate the total current in the semiconductor. Now, Einstein relationship, what is the Einstein relationship? That is dP by mu p. Suppose if I consider that only dP by mu p, that is equals to dn by mu n. Dn by mu n is equals to kT by q, that means equals to Vt. Now, kT by q, k is the Boltzmann constant and T is the temperature, room temperature, suppose we consider, and q is the charge. So Vt means the volt equivalent of temperature. Volt equivalent of temperature. So at room temperature, Vt value is almost 0.026 volt. Okay, because T is equals to 300 Kelvin. If we can put the T is equals to Vt is equals to K into T. So K is the 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, into temperature 300 and divided by 1.6 into 10 to the power minus 19. So that is your almost 0.026 volt if we calculate. Okay, so dP by mu p is equals to dn by mu n is almost equals to 0.026 volt at room temperature. At room temperature. So that is mentioned it here. So thank you for this session, and see you into the next lecture where we will discuss about PN junction depletion region formation. So thank you everyone.